Everything will be recorded. Lectures will be posted on YouTube. We'll see how the slide projection works out. Usually we're in the center here. Well, good morning to everybody. Welcome to Organic Chemistry. Your life will never be the same. I'm Dr. Stevens. Looking forward to getting to know you as we go along. I don't know if you'll continue with Organic 2 here, and not summer, not with me. So maybe just one class here with me. One thing I'll go ahead and say before I forget it is you guys are kind of sitting there with a kind of a clean slate, most of you, 99.9% of you are. When you get over to the end of Organic 2, you're going to be amazed at how much you know, and think back to right now how little you know. Okay? It's a 2-semester sequence, Organic Chemistry, 3411, 3412, and it's a lot, but it's very doable. Main thing is organizing your material, staying organized, staying focused, and not getting behind. In Gen Chem, you can get behind, you have a test, and the next test you move on to different topics. Not in Organic. Test 1, you have a test, and then test 2, we use all that material. And if you didn't learn the test 1 material, then you're definitely not going to be able to learn the test 2 material, that type of thing. Okay, so you cannot get behind. Everything we learn is important because in a week or 2 weeks or maybe 2 months, we're going to be using it. If you can't use it then, well, I'll have to say, well, you need to go back and retake Organic 1 next semester because we've already passed that. Right? Okay. Stuff we covered today will be very important tomorrow and 2 months from now. Syllabus. Everything's here. One thing for me is I don't like to read things to you. Okay? Everything's there. I expect you to read and ask questions. Tomorrow, first thing, I'll say any questions about the syllabus. Okay? If something's not clear, please ask for clarification. Otherwise, I expect you to read as if I sat here and read it to you and said, this is important, this is important, this is important. Everything's important there. I wouldn't have written it there. Okay, textbook. The official textbook is the book by Klein. There's a paperback version in the bookstore, although I see the bookstore does not have any there. Anybody bought something from the bookstore? They don't appear to have the textbooks, but you can get it on Amazon, probably cheaper anyway, the hardback version. The version supposedly in the bookstore is paperback to save you a little bit of money. You do need to have a solutions manual. Of course, you need to be working homework problems, and solutions manual is where you get the answers. You want to check yourself. Very important to do. The one in the lab and the bookstore comes with access to the online system, which that's where you find the solutions manual. Otherwise, I would get a hard copy. For example, this here, you can get those off of Amazon. Okay, but I don't care which textbook you use. You can really use any textbook. They're all about the same. They're called Organic Chemistry. You can let me know. Maybe your cousin or someone has one from a couple of years ago. Probably going to be fine. Just make sure you have the solutions manual that goes with it. All the topics we'll be covering will be just about any textbook. Some will be in few textbooks. Some topics we'll cover will not even be in this textbook. Whatever textbook you have, use the index, find that chapter, subchapter, and read and work problems in the textbook. Okay? Perhaps a little bit different from other classes. I don't want to say, hey, you've got to buy this $300 textbook, and we're going to use it about 5 times. I don't have to waste your money. Okay? You also need a lab techniques book. Lab technique. The one of record on the syllabus is the one by Morag, co-authors. This is where you find your techniques that we'll be using in the lab, like TLC, recrystallization, etc. There are a couple of demo videos on the YouTube website. Please see what's on that site. Distillation and recrystallization. They're hopefully referred to along the way. I produced a workbook lab manual. This is just me. And by the way, I sent out an email about most of this. I've sent you several emails. It seems like some of you have not been getting my emails. Did you not get any emails?
No, sir.
Let's make sure that I have you on the list and see what's going on. But this here, a number of you have this already? Yeah? Okay. Purchased only in the chemistry and physics main office. It's $15 cash only. That just covers the cost of binding and labor to do that. The first half of it is basically like homework problems, problem sets, divided roughly by each test. There'll be 3 tests. Short answer, and then there's a section of multiple choice questions for each test. Please use the table of contents to see what's in here. Also a final exam review section, problems. Then the second half is the lab manual. Okay, the lab manual has overview of lab safety guidelines. Safety is very important in lab. Requirements for notebooks, requirements for lab reports, requirements for checking into lab, which we'll be doing today and tomorrow. You have lab either on Monday, Wednesday, and Tuesday, Thursday, is that right? Okay. Monday lab will be checking in today, 2:30, Science Hall, 3rd floor. The checkout instructions are here, and also check-in instructions are here. Also, the lab sheet that is needed for check-in is there. Syllabus.
Thank you.
Again, this workbook lab manual purchase in the Department of Chemistry and Physics main office. Everybody knows what that is? 3rd floor, Science Hall, west side. Okay, again, I don't like to read things to you. The instructions for checking in are there. When you come to lab, I won't say much other than, okay, check in, guys. Instructions are there. If you have any clarification, please ask. Okay, course overview. Basically, organic chemistry. What is organic chemistry? Chemistry of carbon-containing compounds. That's very simplistic. Huge area of chemistry. Large number of organic compounds, and these can range from just small molecules like propane that you heat your gas grill with, propane, 3-carbon alkane, caffeine, which is in some of your coffee, a bottle of water. Any organic compounds in water? Well, there might be some trace impurities or something. But the plastic bottle is an organic compound. So polymers, plastics, very important. Polymers, huge field, material science. Your big screen TVs have organic compounds in there in the screen to make the image. Drugs. Just about 99% of drugs are organic compounds, and most of them fairly small, 10, 20, 30 carbons. Tylenol. My background is in drug development, medicinal chemistry, and I often use drugs to illustrate organic principles. For example, on the yellow sheet, everybody got the gold yellow sheet? Okay. If you don't have one of these I refer to, please come up and I'll give you one. Okay, we don't really have a... Somebody else need a gold sheet? So you'll see drugs there, singular, okay, antihistamine, typical organic molecule. Okay, so what are the basic topics of Organic 1? You can read there. We'll start out with basic structure, okay, hybridization, charge, Lewis structures, things like that. Structure dictates reactivity, and so you got to know things like hybridization, especially. Nomenclature, we'll learn how to name compounds with some terminology. You got to be able to refer to compounds, rather than just saying, hey, look at that over there. Well, what's the name of it? How do you describe it? Terminology is always important. Resonance, we'll start with resonance early on, and we'll build. Resonance is hugely important. That's a big topic that we sort of build towards. Stereochemistry, functional groups. Okay, functional groups, you have to basically learn them. But as you go along, they'll just become commonplace. Okay. Reactivity mechanisms. What's a mechanism? I remember first thing I heard mechanism in organic chemistry, what's a mechanism? Well, now a mechanism is just like when you do a math problem. How do you do it? That's just your mechanism for doing it. Learning to use use reaction arrows appropriately. Mechanism arrows. Spectroscopy. Okay. Spectroscopy will be very important throughout the course. And on test 1, we will cover IR spectroscopy. Okay. IR is on test 1. Mass spec is on test 3. Actually, test 2 is the only test I give in organic 1 or 2 that does not include spectroscopy. Okay. IR is covered by video only. I sent out an email. Okay. There's 2 videos on the YouTube page. I also sent the IR packet by email. Okay. You have that packet in front of you as you watch the video, because I have that packet up here and I'm referring to it. Okay. So the handout goes with the video. By the way, there's also the alkane nomenclature. That's about video only, and I sent you that also in that email. But that packet is more than just nomenclature. A lot of that stuff will be covered in class. Okay, so your important dates, your tests, 3 tests and then final exam. Grading various things, including recommendations on studying. Please read, there's some websites there. The back of the second page, I think it is our daily outline or schedule. Where are we at? Monday? So, I think we're right here, yeah? Chapter 1 through 2. Lewis structures, functional groups, etc. That's what we'll be covering today. DUS, okay, IR, and this only by video. So here's each day. The lab schedule is on the end. We have lab twice a week, so it's broken into 2 sections. This is what you're doing first day of the week. And this is what you're doing next. So, if you have lab Monday, Wednesday, it's Monday, Wednesday, or it's Tuesday, Thursday. So, Monday or Tuesday, you're checking in, then we have lecture downstairs. Downstairs meaning some room in Science Hall that's available. Before we leave the lab, we'll say, hey, we're going to be down in whatever room. Okay? So check in today and then some type of lecture. We want to make use of our time because summer is quick. All right? And if we have some time that we can utilize, we should do that. Wednesday, Thursday. First lab is solubility testing of organic solids. Okay, you find the lab in the lab manual. Everything's there, it's introduced. Let's take a look at that. There's a table of contents for the lab section, solubility. By the way, we're not doing all these labs. Okay, they may not be in order. This is what we're doing. Occasionally I have students come to lab and they have prepared for the wrong lab because they just did the first one in here instead of the first one here. Okay? Happens to be the first one, it's page 20L. 5 pages are labeled with L. And here we go. I call this the handout. All these used to be handouts. And so what I've done is I've just put them all together in a booklet. Hopefully you'll find that to be organized and convenient and well worth the $15. So we'll be using these 4 compounds. The lab is introduced. Okay. After the introduction, we have, some of this format will vary, but in this one it says pre-lab. So this is telling you exactly what you need to do before coming to lab. Okay. Your notebook, but you also have the notebook section in the guidelines that you should have read, which discusses pre-lab right after the notebook. Okay. So between the two, it should give you all the information you should be doing to be prepared. Now, typically, now this one discusses the report. In many cases, it will discuss the report requirements. In general, every lab requires a report, but I've sort of started also doing instead worksheets or answer sheets. So some will have that. Some will say report or answer sheet, and I'll have to tell you which one we're doing for this lab. Okay? In the end, I'm not going to try to tell you everything here, but in a day or two, I'll say any questions about this, and then we will discuss the things that need to be discussed, or if there were any loose ends. Okay? So, we start by reading it and seeing what type of questions you might have. Typically, your lab report or worksheet is due the next time you come to lab. Okay? But we are doing 2 labs a week. Okay? So, I do want to be sort of aware of, okay, we got a test, so I don't want to have you have to turn in the lab on the same day. So I may delay it, or we'll try to adjust some things, okay, to make it most suitable in our short time frame. So, always be alert. Okay, so we're checking in on Monday, Tuesday, and we're doing solubility on Wednesday, Thursday. Okay. Let's see what else. We want to get going today. I always miss a variety of things. Doing this quickly. In the syllabus packet, there's also, okay. I'll put this in here, it's sort of a little sarcastic way to relay some points. Basically, organic chemistry, known to be difficult, is that right? The main reason it's difficult because it's just a lot of information. Okay, not so much that it's all hard. I mean, there's some difficult parts about it, but the main thing is just you guys tend to just get behind and aren't organized, and before you know it, 2 or 3 weeks will go by. Well, that's a regular semester. If you let 2 or 3 weeks go right in the semester, it's going to be, we're going to be getting close to final exam. So it's doubly important to be organized and on the ball in the summer. That's the main thing. You just let time go by, and then you're too late. But here's some ways. Anybody want to fail the course? No? Good. Okay. Well, then don't do it. Don't do these things. That's basically the don't do page. Please read. I mentioned my background's in drug development. Here's some structures of some common drugs. Okay. Like Tylenol. Okay. First off, we got to quickly become familiar with these line bond drawings. Each point of vertices is a carbon. Okay. We'll get into this. We've got 6 carbons, 7, 8. You know, Tylenol is just 8 carbons. A couple of oxygens, nitrogen, and you've got a drug that's been used for 100 years. Okay. It's amazing. But you can have other drugs, Aleve, Ambien, a sleep aid. And so you may be familiar with a number of these drugs. Anybody work in like nursing or pharmacy or something? Okay, you may recognize some of these. You know, Prozac. Okay, it's amazing how simple the compounds can be, but you know, somebody's making lots of money. But they're also helpful. Here's another page, chemistry of ibuprofen. This sort of gives you an overview of the course as things we'll cover. You can read some of these questions. Hopefully by the end of, when we come to test 1, and hopefully by the end of the course, you'll be able to answer all these. Okay? Right now, it's probably, most of this is a little bit foreign. And then advanced questions, okay? Advanced questions, what do I mean? Well, why are you taking organic chemistry? Can anybody tell me? Here's what I expect the answer to be because I'm required to, because of something. Right? Okay. Well, if that's all the reason you're taking it, then you're all kind of off to a bad start. I would encourage you to say, why do you want to take the course? Why is it important? Because it's required because it's usually important. I would get away from required to, I'm taking this because then I'm going to be more prepared to go on to take biochemistry. Because you can't take biochemistry without knowing organic chemistry. And then why am I want to take biochemistry? Because then I want to go on to be or whatever, because if I'm going to be this, I've got to know science. And guess what? This is the science of most of the careers that you guys want to go into. Okay? And some of the careers may be more, maybe clinical or something. But guess what? I kind of ask doctors sometimes, I'm like, about a drug, and they're like, I don't even know. They just know that the rep told them that this is the best drug. I'm like, kind of would rather have a doctor that knows about the drug, and they're not just reading the label along with me. So do you want to be an informed clinician or whatever, and really know the science? That's why you're taking the course, and you want to learn it. Okay, so advanced questions. These are questions that we're not going to answer in this class, but then you'll go on and talk about maybe biochemistry or pharmacology or somewhere down the road. And this stuff is preparing you to answer such questions. Okay, anybody want to get a job one day? Anybody? We got one. Okay, 1 out of 40 wants to get a job. That's good. This is the job ad. It's about 10, 15 years old now, but if you'll look in here, figure out how to back this boat into the driveway. If you read this job description, it's pretty much the syllabus for the course, the course description. Okay? Must have an understanding of fundamental reaction mechanisms. That's what we're going to be doing. Functional group reactivity, yeah. Familiarity with spectroscopy techniques, including NMR, IR, test 1, mass spec, test 3. Spectral interpretation, all throughout the course, especially in Organic 2, lab. Knowledge of practical and theoretical aspects of synthetic organic chemistry. I mean, you get a job with this stuff. By the way, drug companies pay their employees very well. They have gourmet buffets on site, weight rooms, daycare. I mean, not a bad job if you're interested in that. Okay, we need to get started. Anybody need a green sheet? If you just pass those around. If there's extras, please bring them up at the end of class. You don't need to bring them up during class. We appreciate you if you want to just lay them up here on the way out or something. Unless I need them. Green sheet. Okay, I give you outlines and usually put them on colored paper. Sometimes the other handouts are colored also. The green sheet is our outline. There'll be at least one other outline, maybe 2 others for test 1. This will get us going. First topic is Roman numeral 1, which is what?
Review of atomic structure.
Review of atomic structure. You guys had Gen Chem, right? Okay. That is, there's an expectation that you have learned the prerequisite material and are ready to use it, right? If I get the gold sheet? Something a little bit new I'm trying. I don't know if it's good for summer or actually bad because I don't want to throw too much at you in the summer. Daily questions, okay? A lot of times when we kind of start, I would like to sort of see how we do with the material from yesterday or how we're doing. Maybe I'd like to try a problem. I could choose a random problem, but then nobody else has ever seen it, and then it's all brand new. These are problems that I may say, hey, let's do this one today. Always be prepared to work these, and you should have always worked these. These are additional homework problems, but these are ones that I may refer to. Like tomorrow, we may look at 1 and 2. Okay? This is the limited that you should be doing. Okay? I can say, hey, how did everybody do on number 3? Any questions? Okay? And questions like this similar to this, will be on the test, and this is also the style of questions you'll see on the test. Up the top it says 2 to 3 per day in summer, okay? So, that's the first place to start, but then you also need to be doing plenty of other homework problems. I'll say more about these things tomorrow when we ask about questions on the syllabus. We need to get started with material. Any questions at this point?
We should do these tonight, look at these, look at these tomorrow.
These are questions that you should, yeah, always be.
Try to get familiarized, like, if it's homework.
Tell me again.
Like, we should try to get familiarized with them overnight as like a homework kind of thing.
Yeah. Yeah. To check yourself. Okay. We'll be covering these in class today and tomorrow. Okay. And you need to make sure. Okay. Homework. I don't require homework. Yay, no homework. No good. What I expect of you is you do homework. Okay. I give you the topics. You do homework problems to make sure you master the topic and to prove to yourself that you can do them. Because if you can't do homework, how do you expect to do well on tests? Okay? You have solutions manual, which I said you had to have, so you check yourself. If you sit down and do a problem and you can't do it, then there's an issue. That means you need to go read more and understand the lecture, rewatch the lecture video. Question?
Do you assign, or do you help us choose homework problems to focus on, or do we just have chapter review?
Chapter 1.
Okay.
Uh-huh. And topics. For example, if we cover hybridization extensively today, I'd recommend working problems on hybridization.
Yes, sir.
Makes sense, right?
Yes.
Question?
For the final exam, it says non-standardized comprehensive.
Correct.
What is non?
Well, many people, instructors in Organic 1 give a standardized, made out by the American Chemical Society. Okay, I only give that in Organic 2. In Organic 1, I give my own. Used to not be a standardized one in Organic 1, but about 5 or 6 years ago, one came out, but I don't use it. I only use that in Organic 2. Okay, let's get started. Review of atomic structure. Protons, neutrons. Okay. Carbon. What's the atomic number of carbon? Periodic table? Atomic number of carbon?
6.
Okay, 6. Mass number? 12 or? That's the atomic. That's the atomic. Carbon 12. What else could there be? Carbon 13, yeah. What do you call that number there? What's this, the atomic number? I haven't had Gen Chem in a while. You've had it more recently than that.
Yeah.
Atomic number?
Yeah.
Oh, what's this number?
Isotope.
Isotope, what else do you call it?
Yeah.
Yeah, okay, mass number that works, okay. Problem is, any carbon, once I put carbon, you really don't need that, do you? Because every carbon is 6, okay? So usually not shown like that. So carbon 12, isotope. Everybody know the definition of isotope?
Has different neutrons.
Okay, how many neutrons does this have? What does this have? Number of protons?
6.
6. That was at 6 there. Okay, mass number 6. Yeah. By the way, periodic table, back of your lab manual, workbook lab manual, periodic table. Yeah. I put a clear cover on it so you could see it. I used to put a black cover on it. Okay, number of neutrons. 6. Why 6?
Because we have to add
Because it's equal, assuming this is a neutral, well, yeah. These add up to 12, we're not doing that. These add up to 12, right? Okay, and then what else can we say? Number of electrons? 6, yes, 6. How's that guy? How does this guy over here vary?
It has 7 neutrons.
A 6, yeah, it's got 7. and then 6. The 6 is assuming it's neutral, okay? Number of electrons can vary. But this is isotopes. Isotopes varies with number of neutrons, right? What else we got here? Carbon 14, what's this one?
686.
It must be 686 because the first two got to equal 14. So these are isotopes of carbon. What's the natural percentage of these? This is about 99% roughly. Yeah, what is this one? About 1%. Carbon 14 is us what?
True. Almost.
It's trace, it's in the noise. These are rounded off. This is trace amount, yeah? These are your natural isotopes, okay? That is the carbon in your body, the DNA in your body, proteins. All the carbon in your body, 1% is carbon 13. Okay? 99% carbon 12. So this is the most important or most abundant isotope. Carbon 13 is important when we do NMR. We do C13 NMR. Because only the carbon 13s actually show up in the carbon NMR. What's important about carbon 14?
Carbon dating.
Carbon what?
Carbon dating.
Carbon dating?
Fossil.
Dating fossils? Yeah. It's radioactive, carbon 14 radioactive, and the dinosaurs, the amount of the carbon 14 would stay constant in the dinosaur as long as it's alive, or you as long as it's alive, because the CO2 is being replenished, etc. But once the animal dies, then the carbon 14 is no longer replenished, and so it starts depleting, and we can measure how old something is by how much it has depleted. Any other carbon isotopes? There's actually a carbon 11, yeah? Carbon 11 is actually man-made. It's not natural. What's the difference in it? 6, but its number of neutrons would be what? Yeah, I mean just 5. Carbon 11 is a positron emitter. Anybody take physics? Yeah? Things like that. Very important in medicine. Here's a compound here, organic compound, where this methyl group has been, the carbon has been converted to carbon 11, and so now it's, carbon 11 is also radioactive, but it's man-made. And this molecule with the C11 in it can be used for imaging and PET scans, and also something called, well, positron emitting topography. It's a positron emitter. That's the way it decays. You can get images, and this is an image used to look at Alzheimer's. This is a regular patient, a good brain. This is a brain with Alzheimer's. The compound binds to the beta amyloid plaque, and where you see red, it's a lot of that bad stuff because the compound has bound to it. And the red is generated by the radioactivity of the carbon 11 in that. They used to make carbon 11 over here on Central Avenue. I don't know if they still do, to supply the medical. Okay, how many valence electrons does carbon 12 have?
4.
4. 4 valence electrons. Okay, 2 of those electrons are called core electrons, right? Okay, typically the valence electrons are the only ones that are involved in the bonding. Okay, so we usually talk about carbon and 4 electrons. We're referring to the valence electrons. Now, if we graph the electron configuration of the carbon, what do we have? 1s. What is this? What's next? 2s. And then what's next?
2p.
Is it 2p? How many of those? Yeah. Okay. And so these are your valence electrons, right? And we have, how many of those? 4, right? 4 valence electrons, is that right? We can have something, this looks like a ground state configuration carbon. No? Does that look right? P orbitals, yeah? 3 p orbitals? Okay. This ground state. We will soon talk about hybridized state. When carbon actually bonds, it doesn't bond in this sort of electron configuration. It bonds in the hybridized state. We'll start with this understanding, orbitals, okay? And we'll go from there. Of course, what does the s orbital look like? It's like a volleyball, spherical, with the nucleus kind of in the center there. Yeah? Electron density. P orbital. Dumbbell shape, yeah? Okay. What's the difference between a 2p and a 3p? Okay, next, bonding. Covalent bond. Okay, we'll have to think about breaks. I want to run over and get something in my office, so I want to take a short break. We may have breaks in between, we got 2 hours, we may have a short break, a quick bathroom break or something, but we may not. We may just keep going. Okay, it'll depend on kind of how the flow is going. But let me take a 5-minute break, and we'll be back. Now the camera, I think I'm just going to let the camera keep rolling. Okay. So it's just one file. But 5-minute break, guys.
We had some students, some previous students, they were willing to work there. They said that anytime you ask a question, like you just did, repeat, and they would say, and he drops it. So it's only basically guaranteed I think it's just energy level there. He's farther away than
Oh, yeah, it's like
It's gotta be very energy.
See, then you like other. Exactly. Like, especially like the bigger especially when teaching because I was someone too. No. It's so exciting, right? It's fun. That's what I found. I don't know why.
Oh yeah, I have to go get my workbook because I forgot to have it. And I can do it when I got
You can see that it still looks like a regular.
I have it. I don't know if you know about the guy who did this also, but
You ever showed it to you? Or is it like, is that an access to them? Or you ever showed it?
How many protons for this guy?
52.
Neutrons. 128 minus 52 is 76. Electrons, 52 if it's neutral. Yeah? Everybody know how to use periodic table? Okay. Tellurium, oxygen, sulfur, selenium, tellurium. Okay guys, let's get started. The green sheet tells me where we're at. It should be the same for you. Bonding. Well, that's an important topic. Covalent bond. What's a covalent bond?
Sharing electrons.
Okay, sharing electrons. If we take an H that has one electron, right? Just a neutral hydrogen atom, one electron. It can pair up with some guy, some other one, okay? Maybe another H. Let's put it here. It has one electron, right? These two can come together and sort of pair up the two electrons. and sort of hold hands, and we call it sharing. Yeah? And that leads to, instead we draw it like this. So this is a 2-electron covalent bond, right? So 2 electrons, and we start with a dash. 1 electron from each atom. Holding hands is sort of a way to remember it, yeah? Now, the bond, how do these interact? How does this lead to the bond? Well, that's a huge topic. I mean, there's a book about this thick just on the nature of the chemical bond. Okay? There's a lot of mathematics there. Okay? I don't know how much you did in Gen Chem, but typically you don't do too much. You just say they're sharing. And that's about all we'll do here. Okay? But huge right there. You have a whole class on just that right there. Okay, so we got this here. Now, why do these want to share? What do we talk about? They want to share because they want to become more like. Okay. Why do they want to become like helium?
Fill their outer shell.
That's, yeah. Want to fill the outer shell. What is the outer shell of the hydrogen? What orbitals are we dealing with hydrogen? It's 1s. That's all we have, just 1s. And 1s holds 2 electrons. Okay? Yeah. By sharing, you know, go back to that book, this thick, but this nucleus gets to sort of count both of these electrons for it. And so it's like this H now has 2 electrons around it. But you also say there's 2 around here. It's almost like there's 4 electrons there. There's not, but you get to count the electrons for both nuclei. Yes, and so it achieves the noble gas configuration. And ultimately, now hydrogen has the helium configuration. And practically, hydrogen just needs to make 1 bond to achieve that. I've got a periodic table. I'm sure there's someone around here somewhere. So there's a big gap, yeah, between hydrogen, 1 more electron, and then all of a sudden you're way over here at helium. Okay? So hydrogen only needs to make 1 bond, because every time you make a bond, you sort of get 1 more electron. Okay? But when we get down here, though, the second row, 1 more electron, you're like beryllium. So it needs many more electrons to become like neon. So when we look at carbon, carbon needs how many electrons to become like neon? 4. So ultimately it's going to make 4 bonds, because each bond you make, you get 1 electron that you can count now as your own. In the end, hydrogen makes 1 bond, because that's all it needs to become helium. But carbon is going to make 4 bonds. And so here, we say each hydrogen has a duet of electrons around it. Let's move to carbon. Let's put carbon up here. Now I want to draw this, we're going to end up with here. Leave some work down. I want to leave this here. Carbon, how many electrons? How many valence electrons? We already said that earlier, 4. We're going to put the 4 around like this. Okay? That's the starting point. Now we can make bonds here. For example, we can bring in another H. Let's bring in an H, and it has 1 electron. Let's denote its electron as an X. Let's bring in another H and its electron. See, its electron is going to team up with one of the carbons here, and we're going to do that 4 times. And so ultimately, we have a structure that if we just show those as line bonds, right? 1 electron came from carbon, 1 electron from H. If we go back and look at it, the hydrogen now has how many electrons around it in terms of a shared count? 2. It has the duet. Hydrogen makes 1 bond. How many electrons does carbon have around it?
8.
Yeah, we get to count them all. 2, 4, 6, 8. Okay, so carbon has the so-called octet through the shared. But you see the original 4 was the dots there. And then the other 4 came from the bonding. So this is basic bonding, and carbon makes 4 bonds. And we can sort of put that here. What do we have? 4 bonds. And we'll go ahead and put the 0 lone pairs. Okay? Now let's move, what's to the right of carbon? Nitrogen. How many valence electrons does nitrogen have? 5. It has 1 more. So we're going to put these around here. 1, 2, 3, 4. Now we're going to pair up. Remember, all these guys on the second row want to achieve 8 to be like neon. So how many does nitrogen need through bonding?
3.
3. So we can bring in an H. By the way, not only can we bring in an H, but you can bring in a variety of other atoms too to make a bond. I'm just doing it with H. Bring in an H with its 1 electron. H with 1 electron teaming up with the nitrogen electron, make a shared covalent bond. Now look at this structure. How many electrons? First off, each H has 2. How many does nitrogen have? 2, 4, 6, 8. Okay? Also has an octet. But it only needed to make 3 bonds. And the remaining sort of area here is a what? A lone pair?
Yes.
And I call that LP. Okay? Lone pair. And this is standard bonding for nitrogen. Because now it has the 8, what we call an octet. Okay? The octet sort of is your ultimate what you're trying to achieve here. And so we, instead of drawing those, we can draw them just as dashes to illustrate the same thing, the lone pair. And this is what? 3 bonds and 1 lone pair, right? And what I'm showing up here is typical bonding for these common elements here. Typical. Well, occasionally we'll see some atypical. The typical bonding for nitrogen is 3 bonds and 1 lone pair. What's next after nitrogen going across?
Oxygen.
Oxygen. How many valence electrons? 6. 1, 2, 3, 4, 5, 6. By the way, why do I go around 4 and then start pairing up?
It's just your system. It's a pretty cool way to do it.
The valence shell of these guys has what type of orbital? I just erased the carbon. The valence shell had what? How many orbitals did the valence shell have? You got it on your paper. I erased it. Valence. How many orbitals were there?
It's 3.
4.
4 total. There was the 2s and the 3 of the 2p. 4 orbitals. Basically, I'm putting electrons in orbitals. 4. Then I have to start pairing up. I don't have 5 orbitals. That's the number. That's the orbitals. Okay. Now, how many bonds do I need to make?
2.
Make one here. We're bringing in the H and its electron. We end up with what? Well, we know that guy. What's that? Water. By the way, what do we call this? Ammonia. And this is 1 carbon alkane. Methane. Okay. It's a gas. In the oil fields, a lot of times the methane comes out first, and a lot of times they just burn it off. You see burning it in the oil fields. Water, right? So what a common bonding for oxygen? Yes. But you understand why though? Because we're getting octets here. And this is how. We're starting with a certain number of valence electrons. What's next? Fluorine? How many valence electrons? 1, 2, 3, 4, 5, 6, 7. How many bonds does it need to make?
1.
1. It can make a bond to H with 1 electron. Oh, does that look like a good structure? Does the H have a duet?
Yes.
One bond, I mean, that's simplistic. How many electrons does the F have in terms of a shared count?
Octet.
8. 7 plus. Okay, we get to count that H, that electron from H as one of the F's now. Octet, there you go. And this can be drawn like this, right? HF, hydrogen fluoride. Fluorine has 3 lone pairs. So typical bonding for fluorine is 1 bond, 3 lone pairs. By the way, does it have to bond to H? No. Here's the original F. Okay. Well, maybe it bonds to another F. There's another original F. And I'll draw that one as a X. That's just 7. But see, this one and this one can team up. Right there, yeah. If those teamed up, you'd have a bond. Right? And what is that? And that's F2, right? I mean, that's possible also. And that's how elemental fluorine exists. Okay, so this is standard bonding across, but of course everything under is standard bonding also. For example, sulfur. What's typical bonding for sulfur? Typical bonding for sulfur?
Same as oxygen.
Yeah. Which is on the board, yeah. 2 bonds, 2 lone pairs. Now, as you go down, you start having d orbitals. And because of d orbitals, you can start having some different things. So for sulfur, that's sort of the starting point, but it can also do a little bit different using those d orbitals. These guys can't, because these guys on that second row don't have d orbitals. Okay. All right. So, also what this is a Lewis structure, right? Lewis structure is where we show all valence electrons either as bonds or lone pairs. And that's just from Gilbert Lewis, who showed structures like this and wrote the big book, going on 100 years ago. When I'm erasing, that's often a good time to ask questions. So, did we cover everything under A? Charges. We haven't done charges yet, I don't think. Okay, structures with single bonds. Let's try to get a little bit more complex. What do we have? CH4O. What's CH4? How are we going to put an O in here? Let's start with this. Typically, I would start with the carbon. Well, I would start with bonding the carbon to the heavy atoms, non-hydrogens, heavy atoms. All right? Because we know hydrogen only makes 1 bond, right? Since hydrogen only makes 1 bond, it's not going to be in the middle. It's going to be on the periphery. So in the middle, we're going to have something like this. Bond your heavy atoms. Now, I'm not going to do the dot and the X. We know that's 2 electrons. We can get to this point. Now, I would recommend putting your hydrogens on carbon to start with. If it doesn't work out, you can then adjust or something. And so-called field of valence of carbon. How many H's can go on the carbon?
3.
3. And then, where do you want to put the other H?
Oxygen.
Yeah. Okay. Are we done?
No.
Here's what I would have started with is, anytime you want to draw a Lewis structure from here, we've got to show all valence electrons. Well, you should know how many valence electrons you're dealing with. How many valence electrons are we dealing with? Carbon has how many?
4.
4. H has 1 each, so it's 1 times 4 equals 4. And oxygen has 6 for a total of 14 valence electrons. Make sure your structure has 14 valence electrons when you're done. How many valence electrons on the board here? That's 2, 4, 6, 8, 10. What's missing? 12, 14. Because what's standard bonding for oxygen? 2 bonds, 2 lone pairs, right? Now you can go back through and dissect and do it like we did over there, but just sort of advancing. Okay, so we get this. This, by the way, is methanol. A 1 carbon alcohol. How about C2H6O? How many valence electrons? 2, 4, that's 8. 6 makes what, 14? Oxygen makes. Oh no, somebody's got it. Is it 20? It's not right, let me know. I think it's 20. Okay. Bond the heavy atoms together. Can you go ahead and do a structure for that one? I bond the heavy atoms first, and then I would recommend putting your H's on carbon. Fill the valences of carbon first. Somebody have a structure? Somebody have a Lewis structure? Uh-huh. It's a pretty good Lewis structure. Anybody got another one? Looks different from hers. Doesn't mean it's wrong. Okay, how about something like this? CCO. Yeah, heavy atoms first. Fill the valence of carbon with hydrogens. 3, yeah. How many here? 2. That's 5. We can put 1 here. It looks like it needs it because it needs to make bond. And then what? Okay. Intuitively, that's just kind of the structure. Is that 20 valence electrons? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Yeah, it's 20 valence electrons. Common bonding for everything. Carbon making 4 bonds. Yeah. Oxygen making 2 bonds, 2 lone pairs. Okay. Anybody get a different structure? Yes?
We never had a different structure.
What did you get?
I did the C and then O.
Oh, you did it like this?
Yeah.
Okay, if we put H's here. I'm out of H's though. I've only got 6.
And then 2 more pairs on.
Oh, you put 2 lone pairs there. 2 bonds, 2 lone pairs. Okay. How about that guy? That's also good. We have 2 different structures for a given formula. This one is ethanol. I'll abbreviate that. Ethyl, 2 carbons is ethyl OH, ethanol. Both of these are alcohols. This is an ether. This is an oxygen bonded to 2 plain carbons with no H. Dimethyl ether. Yes. 2 compounds for the same formula. What's the terminology for these 2, the relationship? Yeah, these are constitutional isomers. 2 constitutional isomers. What's a constitutional isomer? Oh, right there. They have the same formula, but different what? Structures. You can say different structures, but it's maybe a little general as we move forward. They have different connectivity. Everybody agree that here the oxygen is connected to 2 carbons, but here the oxygen is connected only to 1 carbon. Different connectivity, but same formula. Constitutional isomers. 2 totally different compounds with different properties. Dimethyl ether is a gas at room temperature. Ethanol is a liquid at room temperature. Okay? Is possible. No DUS. Okay? These have no DUS. Some of this is just sort of statements that only going to make sense in a little bit. But I'll go ahead and make these statements now. We'll cover DUS. These are all saturated because we're not dealing with double bonds yet. It's a shame that Can't combine two rooms and make a great room. The board is good, the desks are good. Structures with double bonds. I'm sort of giving it away, but let's try CH2O. How many valence electrons? Covalent electrons. Okay, we need to make sure our Lewis structure has that. Okay, CO. There's your heavy atoms bonded together. There's only one way to do that. Where do you want to put your H's? Okay. Are we done?
Double bonded to oxygen.
How do you know that?
Carbon has to have 4 bonds.
It has to have 4 bonds, and so
Okay.
it has to be double bonded to oxygen.
Well, I'm glad your answer wasn't because you read it. You could read it, you could intuitively kind of know it, but let's do it sort of systematically, a process, instead of just sort of winging it. Well, I didn't intuitively know it. What's the process? Okay? Well, we don't have any more H's to put up there. We can't fill the valence of carbon with another bond. But we have 12 valence electrons. How many on the board so far? Only 6. We got 6 more to put up there. Here's the process. At this point, we can only put electrons. And we're going to put them up there originally as lone pairs. But let's actually fill the valence of oxygen first. Only putting the H's on carbon, that's just H's there. But ultimately, to satisfy, which one is more electronegative, carbon or oxygen? Oxygen, which means it's more electron greedy, electron demanding. So if we had to put up electrons, which one is going to demand them more? Oxygen. So let's put them there. Let's fill the valence of oxygen with lone pairs. There's 1. So what's that? 2, 4, 6, 8, 10, 12. Can't put any more. There's 12. Is that structure done? Now we can introduce charge. That is a reasonable structure. I mean, it's got 12 up there, all the atoms are up there, but it's missing charge. How do you determine charge? The charge of this oxygen is what? Formal charge. Charge is
-1.
how many it owns, okay, versus how many it's supposed to have. How many valence electrons oxygen is supposed to have?
6.
You knew it up here. 6. Okay. How many does it own here?
7.
It owns the lone pairs, 2, 4, 6. But if this was sort of the dot and the X, we would say 1 from oxygen and 1 from carbon. And so it's like the dot and the X. It owns the dots. It owns 1 of these. It owns 1 of each covalent bond. So it owns 7. Owns 7. Okay. It's supposed to have 6. One more than standard or whatever, or okay. So if you have 1 extra electron, it has 1 extra electron. What's your charge? Electrons are negative, so if you have 1 extra of those, -1. Okay, and usually just a negative sign. Circle. Always circle charges with me. Now, what's the charge of carbon? How many does it own? 1 from each bond, right? How many does it own there? 3. How many is it supposed to have?
4.
So is it got an extra or is it missing 1?
Missing.
It's missing 1, and if you're missing a negative charge, you're
Positive.
yes, it's positive. It's net neutral. How do we know this is a net neutral compound? Well, I know these are canceled to make, but how do we know that it's supposed to be net neutral?
There's no charge on the formula.
Exactly. There's no charge here. If this was a charged compound, I should have showed you the charge when I gave you the formula. I can't not show it to you. It's neutral. So there it is. It's net neutral. Plus and minus cancel. If it was only negative, I should have showed you a negative in the formula. Okay? It's net neutral. There you go. You like that structure? That's not a bad structure. But octet rule is one you want to kind of meet. Does carbon have an octet? 2, 4, 6. It doesn't have 8. We can get the carbon another bond by the oxygen sharing some of these electrons. And here where we're going to do our first mechanism with the use of an arrow to show electron movement. If we take these electrons, I circled them, and move them in here with an arrow, what this is illustrating is these two electrons fall in between the C and the O to make another bond. And whenever we just move electrons, we use a resonance arrow. And that's going to give what? We now have the carbon with 2 bonds between oxygen, 2 lone pairs. Why only 2? Because the third one moved in to make bond between. And then over here. Now we can draw these any way you want. We haven't talked about bond angles yet. We'll do more appropriate bond angle. But we get to this. Now does the carbon have an octet? The answer is yes. Because, how many bonds are around the carbon? 4. A double bond is 2 bonds. Okay? What's the charge of the carbon? It owns one of each bond. It owns one of these, one of these, one of these, one of these. It owns 4. It's supposed to have 4. It's neutral. How about the oxygen? What's the charge of the oxygen? It owns how many?
6.
Yeah, it's supposed to have 6, okay? All neutral. Carbon has octet, which is usually something you want to try to achieve. So the process we did here was we put the electrons up, then we moved them in, and we got to the good structure, the better structure. Why is that structure better? The reasons I put on the board. Everything has an octet. Both of these are now standard bonding. 4 bonds, no lone pair. 2 bonds, 2 lone pairs. Right? Standard bonding for oxygen. 2 bonds, 2 lone pairs. This is not bad though. This is a resonance structure. Okay, we could say more here, but let's move to the next one. By the way, this has 1 DUS. A DUS is basically right here. When we start making the double bond, that's just something for your notes right now. We'll cover DUS in a little bit. Okay, let's try HCN. Valence electrons, 1, 4, and 5 makes what? 10 valence electrons, carbon to nitrogen. Where do you want to put the H? I recommended carbon. That's sort of an arbitrary recommendation, but just do that. Okay? Can't put any other atoms up. Can't make any more single bonds to new atoms. 2, 4. We have 6 more electrons. That's 3 lone pairs. Where do you want to put the lone pairs?
Nitrogen.
Yes. How many lone pairs?
Just 1.
Standard bonding is 1, but we're doing a process here. We want to take care of the nitrogen first. How many does nitrogen want?
6.
It wants 8 electrons. We're going to fill the valence of nitrogen first because it's the most demanding. Does nitrogen now have an octet? Yes, 2, 4, 6, 8. It's not standard bonding, but it's got the octet. We took care of it. 10 electrons. Can't put any more. Okay, how about charges? What's the charge of the nitrogen?
+2.
Not +2. How many does it own? 2, 4, 6, and one of these it owns 7. It's only supposed to have 5.
-2.
Sometimes I put -2, sometimes I put 2 minus. I don't know, because usually you don't have any, usually in organic chemistry, you only deal with +1 and -1. So it's rare that you're going to have +2 or -2. This is sort of just our process. What's the charge of carbon? +2, because it only owns 2. It owns one of those and one of these. Okay, how can we make this better? Question?
No, just triple bond it to the carbon.
Well, but process. Let's do process. So when you're doing homework, how did you know triple bond?
Because you have to fulfill the octet rule on both of them, so you have to take 2 lone pairs and put it towards the bond towards the carbon.
I generally agree with you, but you seem to be just sort of thinking intuitively. And when you get to some crazy example, I'd rather you have a process. Ultimately, whatever works for you. But the process that I'm trying to show you is, hey, this guy needs some electrons. It's only going to get them, we can't put any more up here. So that we're going to have to ask that guy to share. And so we're saying, hey, move these in here. And let's do it stepwise. And since we only moved electrons, what's the new structure going to look like?
2 locations, C double bond.
HC, now it's double bonded to N. How many lone pairs on N?
There's
Only 2 now, because one of them moved in. We've got this new structure. It's a resonance structure. What's the charge of nitrogen now? Just negative, and the charge of the carbon?
Positive.
Just positive. Okay, is that a good structure? No. We got to ask nitrogen to share some more. So let's take these electrons and move them in. And what does that lead to? Now we get the triple bond. How many lone pairs are remaining on nitrogen? 1. Charge of the carbon now? Neutral. Ah, look at the carbon, 4 bonds. Look at the nitrogen. 3 bonds, 1 lone pair, which is standard for nitrogen. Now we have arrived at the good structure through more of a process. What's the best structure on the board? This one. Everything has an octet, and there's no charges. Charge separation is not best when you can avoid it. This is a typical best structure for HCN. And we have triple bond, which is going to be 2 DUS. Got 2 extra bonds. We'll define that a little bit. Okay, and it looks like we're ready to do that now. Degrees of unsaturation. Handout, functional groups and DUS warm-up. Anybody not have that handout? White, at the top says functional groups and DUS. Okay, the warm-up questions are sort of like the daily questions, that sheet I gave you. Other questions? The idea for the warm-up questions is to have looked at them ahead of time. Obviously, you're just getting this today. And so you come prepared for lecture, okay? So I give you some questions to think about. This also sort of sets the stage. This is what we want to be able, sometimes what we want to be able to do when we get done with these. Sometimes I may supply you with the answers to the warm-up questions, or sometimes I may not. Okay. By the way, we just did that structure. Okay. How about this structure? C16H13Cl N2O. Could you put one together real quick for that? A little more complicated, yeah, than just HCN or CH2O, yeah? Okay. DUS is something that's very useful, okay, just sort of as a starting point. Take stock of what's going on. I think we can look at DUS now. It's a couple of pages over. DUS, DUS can be determined two different ways. You need to know both ways. One from structure and then one from formula. Okay? We'll start with structure. One double bond is one DUS. I already sort of wrote that for when we did the double bond. Okay? One triple bond, that's my TB, it's TDUS. Ultimately, each pi bond is a DUS. We haven't talked about pi bonds yet. That's ultimately what it is. And also, one ring is a DUS. A DUS is a degree of unsaturation. Some textbooks call it an index of unsaturation. It may be a little bit different term. Okay. DUS is sort of universal. We did ACN has TDUS. And when we do formula, we'll see that it's missing 4 from max. We sort of do structure and formula kind of together here. For example, consider this. We got a carbon and nitrogen. This formula here, by the way, sometimes when you see formulas, there kind of have some information built in. There's some bonding information here. We could show this as CH5N. This is pure formula where it's CH and then alphabetical. But you may also see like this. This is where there's a little structural clue kind of given to you. Okay? But I still would call it formula. C and N. But here with the C and N we got 5 H's. Where there we only had 1. You see, a C and an N can support 5 H's. And this is with 5 H's there. And we say it's totally saturated with H's, because you can't put any more. And that's what saturated means, saturated with H's. Where, if it's only got 1, we say, hey, it's not saturated with H's, it's only got 1 when it could have 5. Okay? Well, it's missing 4. It turns out that each 2 that you're missing is a DUS. That's sort of getting into more formula. But look at this. We could have this structure. That's 1 DUS. Remember the pi bond, the double bond, right? You see that? But also, for 2 carbons, we could have 6 H's. That would be totally saturated. 0 degrees of unsaturation. No saturation. We're missing 2 H's, so it's 1 DUS. It's 1 degree of unsaturation. You can also get this from rings. For example, if you have 3 carbons, the maximum number of H's would be 8, and that would be saturated. If we make a 3-membered ring, that is, the 2 N carbons are bonded to each other, well, then this can only support 6 H's. So we're missing 2 compared to that, and every 2 you're missing is 1 degree of unsaturation. So essentially, a ring is also a DUS, because the only way to make a ring, if you want to make this a ring, you have to get rid of 2 H's and then bond the 2 carbons together. Okay? Here's ibuprofen, and the structure got whole. Boom, boom. How many DUS? Now also you'll learn that when I draw my benzene ring, I typically boom, boom, boom. And my bonds aren't very clear, but it's double bond, double bond, double bond, right? Okay.
5.
Can you tell how many is there?
5.
How many double bonds do you see?
3.
3, 4. And then how many rings?
1.
1. The DUS is 5, yes. Should be right. Yeah. And that's just bookkeeping at this point. As we move along, the usefulness of this will become more apparent. Okay, from formula. Also, a lot of my handouts, I'll cover the majority of here. Okay, other stuff is just sort of the second reading. Everything's important. If I miss something that's on the page, just ask. but I'm not going to read every single word to you. I'll hit the highlights. Okay, from formula. First off, hydrocarbon, which is a compound that just contains hydrogen and carbon. We call that a hydrocarbon. CH only. It turns out that the maximum number of H's, which would be saturated, can be determined by this simple formula. 2n plus 2, where n is the number of carbons. For example, look back up here. I quickly knew that was 8, although you could count them, because that's 3 carbons. And if you put in 3 here, 2 times 3 is 6, plus 2 is 8. So I knew that since there's 3 carbons, and it's saturated. I can tell it's saturated because I don't see any pi bonds or rings. I quickly knew that it was 8. Okay? That just comes from, well, we fill in the valences, and carbon makes 4 bonds, and it ends up being a nice little formula. Okay. Now, C5 would be, how many H's would be saturated? 12. Okay? Now, since we know C5H12 is saturated, let me ask you this. Can this compound have a ring?
No.
No, because if it had a ring, it would have a DUS, and that means it's missing 2 H's compared to saturated. So that tells you that can't have a ring. Can this compound have a double bond?
Yeah.
See? It can't, because it's saturated. So this is sort of the power of understanding DUS and what it can tell you. So already I know that it can't have double bonds. Let's look at this one, C5H10. First off, is that saturated?
No.
No, because saturated would be H12, because 2n plus 2 is 12. How many is it missing from max? Missing 2. Every 2 you're missing is 1 DUS. That's stated here. So, can this compound have a ring? How many rings max can it have?
1.
Yeah, you can't have 2 rings, but you can have 1. Can this have double bonds?
Yeah.
You can have 1, but it can't have 2. Because to have 2 means you would have to be missing 4 H's. Okay? Please read and understand. I think Prozac's on the bottom here. How do we deal with heteroatoms? Heteroatoms meaning non-carbon, also non-H. Heteroatoms can also be called the heavy atoms, non-carbon, non-H. It's just a kind of a slang term. Prozac has this formula. How do you deal with these heteroatoms? Well, here's how you do it. Oxygen, you just ignore. Turns out you just ignore it. Ignore it. Halogen counts as a hydrogen. How many bonds does hydrogen make? 1. How many bonds does a halogen make? What is a halogen? Fluorine, chlorine? Yeah. 1. See, they both make 1 bond, and so they sort of have identical bonding almost. Nitrogen, you actually subtract an H. You can look at Y and all this, but that's it. So, if this is the formula of Prozac, we can turn that in to just this by doing what? Okay, how do we treat Fs?
As a hydrogen.
Right, so let's get rid of this and change that to 21. Like that's 3 H's, because we count it as hydrogen. What do we do with oxygen?
Ignore it.
Just ignore it, don't do anything. What do we do with nitrogen?
Subtract 1.
Subtract, so this goes to what? 20, which is what I got written there. So that's, okay? Now you got to be careful because nitrogen subtracts an H this way, not the other way, and I can't explain the other way. Sometimes you guys go backwards. When that comes up, I'll point it out. Okay? Here. So, knowing that this is it, the answer's already there. 17. What's saturated for 17 carbons? 2n plus 2. You guys have math? 2n plus 2 is 36. 36? 36. Okay. Is that 36?
No.
No. It's missing. How many is it missing?
16.
Missing 16.
So 8.
Okay. How many DUS?
8.
8 DUS. You basically divide that by 2, because every 2 you're missing is a DUS. Okay, a DUS. That's what we got here. Okay. Where's the structure of Prozac? It's on the, I believe it's in the syllabus. Was it? Yeah, right. Syllabus drug page here. Okay. Do you see the 8 DUS? How many pi bonds?
6.
6. How many rings? And that is 8. So we just did it from formula. We can also do it by looking at structure. Okay? Questions about DUS? Formal charge. We actually already did formal charge when we were doing the couple of those structures. Yeah? Carbon with 5 bonds, not on the planet. How about silicon, phosphorus, sulfur? Well, those are the ones that, if it has d orbitals, those guys can expand their octet, and you can have a sulfur with actually more than 8 electrons around it. Okay? For example, if you look at the most common Lewis structure of sulfuric acid, you see the sulfur has 2, 4, 6, 8, 10, 12 electrons around it. Okay? But the oxygen, though, can't do that. What's typical bonding for oxygen? These are all typical oxygens. 2 bonds, 2 lone pairs. All right? Okay. Functional groups. Oh, resonance. There's a comment on resonance. We started doing some resonance here. Okay. Definition of resonance is there. When more than one acceptable Lewis structure can be shown for a given arrangement of atoms. Please always be thinking about resonance. Always important. We'll actually allude to it along the way. But it's actually not covered until test 3. But once we get over there, we'll have laid a lot of foundation. Functional groups. Functional groups is in the same handout with the DUS. Should be. Second page. Okay, functional groups are just sort of standard, common arrangement of atoms that you will see. The first here are your hydrocarbons, compounds that just contain hydrogen and carbon. Alkanes. Alkanes are just saturated hydrocarbons. Saturated means what? No. A saturated hydrocarbon has no what?
DUS.
Has no DUS, which means it has no
Double bonds or rings?
double bond. Actually, rings though. A ring alkane is probably going to be called a saturated hydrocarbon. That's unfortunate. Shouldn't even bring that up, but yeah. Okay, an alkene. The ene ending has the carbon-carbon double bond. That's called an alkene. Okay? You say, hey, look at this alkene here. Carbon-carbon double bond. So this is a degree of unsaturation. An alkyne with the YNE ending has the triple bond. Carbon-carbon triple bond. Okay? And you, of course, will see that this is standard bonding. Carbon is making 4 bonds. Okay? That's an alkyne. Now, to have a carbon-carbon triple bond, you've got to have 2 carbons. You've got to have 2 carbons to make this. You don't actually have to have 2 carbons to make this, because you could just have CH4. That would be just methane. So methane would be your simplest alkane. That's why it's called methane. When we do nomenclature, you'll see that the prefix, the meth, that indicates 1 carbon, and then the ane indicates what type of compound it is.
Does the R group have to be a carbon?
Good. R group is a very important terminology. Well, yes, because we're just dealing with hydrocarbons.
Oh,
Now, once we get going, things will loosen up a little bit, but yes, R group. I was glad to use that term. It's important. Understanding R groups. Okay, let's move to functional groups that contain heteroatoms, things other than carbon. And okay, your alkyl halides. This is going to be a carbon group that is bonded to a halogen. Now, R is typically any type of carbon group. It can be 1 carbon or it can be 68 carbons. All right. It's generic for a group of carbon chain. Why R? Because there's no R on the periodic table. Not just a single R. As an example, we could have R being methyl, just a 1 carbon, and we could have something like this, and that's alkyl halide. By the way, you may see structures shown sort of condensed a little bit, not fully appropriate. It looks like these H's are bonded to the bromine, right? See that? That's just sort of shorthand condensed. Really, these H's are over here, yeah? And it's bonded to bromine, and the bromine has lone pairs. Okay? Another little tidbit. A lot of times you'll see structures and the lone pairs aren't shown. This is because I didn't feel like drawing them, or the book didn't feel like drawing them, but okay. You kind of know they're there, and as we go along, that type of thing will just become a little looser, and we'll only maybe draw them in when we want to focus on them. Okay? Ultimately, though, if you're asked to draw a Lewis structure, like in an official manner, hey, show a formal Lewis structure, I would put you got to make sure you put the lone pairs. Okay, an alcohol is a carbon group that has an OH. And at the beginning we had, see, I want to draw the H's like this. You know, it's just quick shorthand. But we had like methanol at the beginning. It was a carbon group with an OH, and with alcohol. Okay. We also showed one like this. We showed dimethyl ether. And ether is an oxygen bonded to 2 plain carbons. The R groups can be just 1 carbon, or it can be long chain. An amine is an R group bonded to an NH2. That would be an amine. But then we can look over here at the nitrogen. These H's can be replaced with R groups. And you can have a primary, secondary, or tertiary amine. With this indicating how many R groups are on the nitrogen. So a tertiary amine would have 3 R groups. Okay? And that's sort of condensed. But we could have maybe a nitrogen with like a CH3, a CH3, and a CH3, a little pair, and that's a tertiary amine. Okay? A thiol is analogous to an alcohol. Sulfur is under oxygen in the periodic table. Sometimes thiols are called mercaptans. I don't know if you've heard that in biology or, okay. Sulfide is analogous to an ether. 2 R groups, ether. Sometimes sulfides are actually called thioethers. The thio being kind of slang for sulfur. So, thioether. Yes, functional groups do need to be spelled correctly. Because on quizzes and tests, you get these spellings and it's like, okay, when do I start counting them wrong? Okay? And so ultimately, it needs to be spelled correctly. Well, yours was spelled so wrong, it wasn't even, you couldn't even recognize it, and, okay? So, please look at your spelling of your functional groups. Okay, these guys over here contain the C double bond O group, which is called a carbonyl group. But caution, carbonyl is not a functional group, it's a component of functional groups. Okay? All these contain a carbonyl. Your aldehyde has the carbonyl with H on one side, methyl on the other. I'm sorry, not methyl, R group on the other. Could be methyl, but it could also be methyl, butyl, propyl, whatever. Ketone has R groups on both sides. And acetone being very commonly used in lab. That right there is acetone. Also fingernail polish remover, most commonly acetone. Carboxylic acid has R group on one side, OH on the other. Carboxylic acid. Now I know over here they're calling functional group carbonyl too generic. These others are sort of important because this is called a carboxy group. The ester is where you have this set up here, but then the oxygen, instead of an H, contains an R group. Let me make a note back over here. Something back over here with the amines. Alcohol, oxygen with one R group. You put another R group on it, it becomes an ether. Right? That's not the way with amines. One R group. If you put another R group on here, does it change its name? Still an amine, it's just called secondary. If you put a third one, okay. You put additional R groups on nitrogen compounds, it still remains the same functional group. Okay? But with oxygen compounds, the trend is, I think, you put another R group on and it changes its name. So that's what we're doing over here. We're sort of putting an R group on the oxygen of the acid, but it changes its name to an ester. Now, amides, now some people say amide, I say amide, some people say amide, some people say amide. I say amide. Amides have the carbonyl R group on one side, nitrogen on the other. Now, if you start putting R groups on the nitrogen, it still remains an amide. You just call it primary, secondary, tertiary, depending on how many are there. With this carbon counting as 1, then 2 and 3. Okay? So that is a primary amide. Acid chloride is kind of unique. For here, we'll see them in organic 2. That's carbonyl, R group on one side, chlorine on the other. And with the halogens, the chlorides are the most common. The other ones are pretty rare. That's why that's there. There's a couple of others that I want you to know that aren't on this particular one. By the way, a lot of the handouts I use don't come from Klein. Some of them do. I use a variety of books. One is a nitrile. That's the C triple bond N with the carbon containing an R group. Maybe something like this. Nitrile. The group itself is called a cyano group, but these terms are kind of used interchangeably. Note that it is cyano and not cyanide. Cyanide would be the anion. I means anion, typically. Another one I want you to know is sulfonamide. This has got the sulfone, O, R group, and then nitrogen. And then you can substitute the nitrogen, have primary, secondary, tertiary. So we could have something like this. Sulfonamides are actually in a lot of drugs. Okay, a lot of your anti-diabetic drugs, diuretic drugs have sulfonamides. Now, it's actually a type of amide or amide. But this is, the long term for this is carboxamide. This is a carbonyl amide. It's usually shortened though. Where here, this is a sulfonamide or sulfonamide. And you don't shorten that one. But it is analogous to the regular amide, except we just change it to the SO2 instead of the carbonyl. Okay, so there's some examples using drugs. We need to go back here. So take a look at these here, yeah? How are we doing on time? What time are we doing? Decent place to end. Some functional groups are identified here, yeah? For practice, okay? Here we go, guys. A lot of times things are written. I may not always point them out. We don't have time. You see something like this, you need to sort of do it. Okay, functional groups over here. If you have any questions about it, we'll see how we're doing. And then we have the outline. Functional groups. Looks like we're ready to start Roman numeral 4, hybridization next time, tomorrow. Please be looking ahead. Okay? It's best if you've done a little reading, even form some questions. What do I need to be looking out for when he talks about hybridization? Any questions before we end? Some of you are checking in the lab today, right? Check-in instructions are in the lab manual. Question?
Do you need to bring me like lab stuff? That's to the first